Lado Iberico. It's not Portugal, it's like Spanish, but I recommend you to have lunch there. And so let me start my talk. Emerging cluster and molecular structures of exotic beryllium isotopes in the ab initio Nuclei Monte Carlo shell model. So this is outline of my talk. So I'd like to briefly sketch Nuclei ab initio Monte Carlo shell model. Then this is just a reminder about the carbon isotopes. And the main subject is here, beryllium isotopes, clusters, and excess neutrons. Here are the collaborators, but this work has been done mainly by Yoshida, this guy, Abe, this gentleman, and also this young guy. And also Shimizu-san, Itagaki-san, Utsuno-san, Ueno-san are collaborating, as well as James Barry and Peter Morris. Okay. Yes, here I'm showing two types of shell model calculations. One is conventional. In the conventional calculation, you obtain a matrix of the Hamiltonian for all possible many-body basis vectors, which are usually theta determinant, and diagonalize this matrix. Well, if this matrix is reasonably large, then it's okay, but there are some limit like this. So beyond this limit, it's very difficult to diagonalize this Hamiltonian matrix. So for bigger problems, we can take this Monte Carlo shell model. So in this case, you can optimize many-body basis vectors, and you can pick up only important ones for specific eigenstates. So then you end up with about 100 basis vectors. They are all optimized for the problem you are trying to solve. Okay, this view graph shows how our eigenstate is expressed. So this is our eigenstate that is expanded by this basis vector. And this basis vector is nothing but theta determinant, but each single particle state is not a simple one. Each single particle state is already superposition of original single particle states. And this is number of single particle states. So this summation runs from 1 to NSP. And okay, this must be a creation operator, and this is some coefficient. This coefficient forms a matrix called D, and then this basis vector is specified by the matrix D. We have several basis vectors from number 1 up to number NB. So this superscript n runs from 1 to NB. And for each of that, we have this has to be n, sorry. And this is amplitude. And this part is projection operator. And because this theta determinant is deformed theta determinant, so it doesn't conserve any quantum number. So you have to project out this state onto your angular momentum, your parity, and so on. And then the expectation value of this eigenstate is written in this way, and this is entirely depends on the choice of matrix D. So the selection of matrix D is so important, and we select it in this way. So suppose we are trying to fix the first basis vector, and then there are two steps. In step 1, we shift randomly matrix element of D. Then initial guess can be taken from Hartree-Fock or some other simple calculation. Then the select one producing lowest ED, yeah? By having this random shifting. And once you come to some reasonable result, then you can polish this D by means of conjugate gradient method variationally. So it's a combination of stochastic sampling, finding some good guess for the optimized D, but this D is not fully optimized, then you make it really optimal by having this kind of variational method. So you can combine these two steps, and you can repeat these two steps for additional basis vectors. Then you obtain basis vector number 1, number 2, number 3, but always the energy is monitored after angular momentum projection and parity projection. So it's like VAP for each basis vector. This is just a sort of implication of this method. So many years ago, Wigner mentioned this kind of things according to David Bernier. Actually, this was maybe transcribed by this person. So Wigner made some speech in this conference many years ago, and he mentioned that maybe we can calculate nuclear property by some great calculating machine, but the result tell us physics. So he requested to produce a vivid picture of behavior of the wave function. And our Monte Carlo shell model has this kind of function indeed. And then this Monte Carlo shell model can give you direct visualization of fully correlated wave functions. That is called T-plot. Let me explain it first. Yes. So this is about the T-plot. And let me start with this potential energy surface. This is the standard potential energy surface of the Hamiltonian we are dealing with. And this example is nickel 68 ground state. So the potential energy surface is like this, and the blue part is lower energy, so it's very low here, but also a little bit low here. And this axis is deformation parameter beta 2, and this angle is triaxiality parameter gamma. Yeah. Then your eigenstate is expanded in this way, and this is our basis vector. So each basis vector has own quadrupole moment. So you can calculate this quadrupole moment, and you obtain Q0 and Q2, and from Q0, Q2, you obtain beta 2 and gamma. So that then we can pin down each basis vector on this potential energy surface, having this beta 2 and gamma. For instance, this guy is one of the basis vectors, and it should have this beta 2 and this gamma. So the location of the circle indicates quadrupole deformation of unprojected Monte Carlo shell model basis vectors. The size of the circle indicates the overlap probability between each basis vector and eigenwave function. So by having beta 2 and gamma thus obtained, you obtain a partial labeling of many-body basis vectors. So in this way, the Monte Carlo shell model could be a partial answer to this request from Wigner. Okay, then we apply this Monte Carlo shell model to some problem in some ab initio way, and also within the framework of no-core shell model. So as you know, the no-core shell model means that there is no inert core and all nucleons are activated. Ab initio means nuclear-nuclear interactions are fixed prior to the study based on fundamental properties and so on. Yeah. And in the Monte Carlo, in the no-core shell model, you have to include many shells like this. So this is harmonic oscillator shell, and in the usual calculation for light nuclei, you just take this lowest shell or next one S shell and P shell. But in our calculation, we usually obtain, usually take 7 shells. That means 0h bar omega, 1h bar omega, up to 6h bar omega. So within this large shell space, nucleons can move around, and then we try to solve Schrödinger equation like this. And in the following examples, the nuclear-nuclear interaction is taken to be Gs16 for beryllium isotopes and radium-16 for carbon isotopes. This is a little bit older, and we did some calculation for beryllium isotopes, so we keep using this. But for carbon, radium-16 is used. Yeah. So this shows how calculation goes as a function of number of basis vectors. So this is first vector, and then the second and the third, and so on. So by including initial 5, that is 6 harmonic oscillator shell, you obtain this kind of convergence of the ground state energy. So this is the normal presentation of the convergence. But also we also developed convergence in terms of energy variance. Energy variance means this quantity. Here is Hamiltonian squared. We can take expectation value of it, and you can subtract H expectation value squared. So if you come to the exact eigenstate, this is 0. That is here. So you start from here and approach it this way, and then result shows this kind of lowering, and at the end you should have this value as a converged value. And if needed, we do this kind of plot, and we obtain estimated value at the extremely large dimension. So the calculation has been done with those supercomputers, and this is a dimension of those problems, and well, it is shown as a function of year. So when shell model started, it is very small, but those are SD shell nuclei, PF shell nuclei, and then we come to ab initio no-core calculation, then the carbon-12, oxygen-16, they need huge Hilbert space, and that our Monte Carlo shell model can deal with those problems. And some systematic studies have been published already 4 years ago for the helium-4 up to oxygen-16 for n equal to the nuclei. But today I'd like to discuss neutron-rich beryllium isotopes. Now let me move on to this part, that is carbon isotopes. And the result I'm showing has been already published 3 years ago in this paper. And this is energy excitation energies of carbon-12, ground state, first 2 plus, and first 0 plus excited states. This is our calculation. First of all, this 2 plus energy appears almost exactly at the energy of experimental value. So this calculation is produces very precise value. And also, if you look at this BE2, from this 2 plus down to ground state, it is 7.65, and experimental value is 70.63 plus minus 19. So, and this value was obtained with just free nucleon value. So this shows the ab initio approach really works for this kind of strongly deformed nucleus. In fact, this case corresponds to beta 2 is equal to about 0.6 oblate, and this large value is really reproducing experimental value. And so, but then we can look at Hoyle state, where Hoyle state may need a slightly bigger model space. In fact, this is a convergence pattern as a function of energy variance. So the ground state and 2 plus state, we can really come to some point very close to experimental value. But for Hoyle state, we are a little bit too high. That means this initial truncation, this may not be enough. So Hoyle state, we may have to go to initial equal to 8 or 9, but present computer resource doesn't allow us to do such calculations. So we have to deal with this. Now let me show you density profile. So this is density profile for alpha particle by using the same interaction. So the highest value is like 0.24. And if you look at the ground state density profile in the body fixed frame, I'll come to this definition later. So in the ground state, you have this plateau with density almost equal to this density. Yeah? But if you look at the Hoyle state, you have 3 separate peaks, and each of them shows similar density like this. So the Hoyle state is really look like 3 alpha clusters sitting a little bit far away from each other. Now let me come back to the come back to the T-plot. Yeah, I mentioned the T-plot, and this is the potential energy surface of carbon isotopes. And usually, this T-plot circles are concentrated in a small region. However, carbon-12 is very special. So in this case, this T-plot circles are scattered over wider range. Then we decided to divide potential energy surface into 3 regions. Region 1 means beta 2 is smaller than 0.7. So this line or that line, so inside this line is region 1. Yeah? Then the region 2 is outside this region, but also this region is divided into 2 parts. One is the triaxial part like this, and region 3 is this part that is only near prolate shape. So the ground state is composed of T-plot circles, mainly here, but a little bit here. And the Hoyle state is mainly here. And the third Doppler state is mainly here. So that means third Doppler state is prolate shape with large beta 2. That means this is like a rod. But here you have very widely spread T-plot circles, and that actually corresponds to this triangle distribution. And here the circles are more densely packed, and that's consistent with this kind of things. And this is rather close to nuclear matter density profile with a little bit lower density at the center of the nucleus. Actually, this lower density at the center is consistent with electron scattering data. So, to summarize the carbon isotope case, so this is a calculation obtained with region 1. Then you obtain this state, and region to this state. But then by having more state, then ground state comes down from this value to that. And that means there's about 6% mixture of this configuration. That means even the ground state contains 6% of 3 alpha cluster component in it. Then if you look at the Hoyle state, this kind of configuration and this kind of configuration are sitting here, but they repel each other, and finally the Hoyle state comes to here. So then finally the energy difference between this one and that one is about 10 MeV. That is slightly higher than the experimental value, but it's still below the neutron threshold and so on. Yeah, sorry, alpha threshold. So, and this is very interesting because even the Hoyle state contains nuclear matter type component with 33%. So the nuclear matter type component and clustering component are not completely separated, and both of them are included in ground state and Hoyle state with different probability. That is quite interesting, and this has to be verified experimentally. I don't know how to do it, but it's very interesting subject. Yes. Now let me move on to the beryllium isotopes. Actually, although this paper was mainly about carbon-12, but also beryllium isotopes were discussed. And about the beryllium isotopes, there are many works in the past, but our initial approaches are rather recent. One is by Anna McCoy in this paper, and she reproduced experimental level scheme quite nicely with region 16 interaction. And this year, Shen and other collaborators published this paper, and they have shown how this deformation spots are distributed over a kind of potential energy surface. So having those results in mind, let me show you our result. Yeah, overshoot it, yes. So first of all, this part is our energy levels for beryllium-8, beryllium-10, beryllium-12. This figure was still taken from this paper, and you can see a reasonable agreement with our calculation and experimental data. Well, usually, always this 2+ energy calculated is a little bit higher than experimental energy. That means this region 16 interaction may not be strong enough to produce large deformation, but otherwise it's quite nice. And also, I learned that experimental 4+ state is around here, so the comparison is still good for beryllium-12. And for the 0+ state, our value is a little bit higher experimental values. And this is B2, and for B2, beryllium-10 and beryllium-12 show reasonable agreement with experimental data. And for beryllium-8, there's no data yet, but green function Monte Carlo calculation is here, and our calculation is here, so they are rather close to each other. So we hope this large change from here to there is a real phenomenon. Now, coming to beryllium-10 and 12. So the cluster structure in beryllium-8 is basically trivial. I'll show you in the next page. But what about the others, right? And another interesting point is how excess neutrons are configured in the beryllium-10 and 12. And in this case, pi orbital and sigma orbitals are interesting viewpoints. So our results are given in this way. So this is a Monte Carlo shell model basis vector, and each eigenstates are given in this way. Yeah, and after angular momentum projection of this thing, then you obtain completely isotropic density distribution. That's the definition of 0+ state in the laboratory frame. But what we'd like to know is not this one, but something like this. That snapshot of the intrinsic state in the body fixed frame. And to obtain that kind of things, we introduced some other method. Oh. So for that purpose, as you know, we can calculate quadrupole moment matrix for each basis state and diagonalize it, and then we define z, y, x axis like this, and then we align those axes so that all basis vector have common z-axis, y-axis, x-axis within this order. I mean, the z-axis is the longest, and x-axis second lowest, and y-axis the shortest. Yeah, and that superposition is called Q-aligned state. And let me, namely, originally we have this kind of basis vectors, and with this you can calculate energy eigenvalue or electromagnetic transitions, okay? But to grasp intrinsic picture that is important for our understanding, we align all those states so that each intrinsic quadrupole moment have the same axis structure like this. And after doing this, we obtain this density distribution. So for your reference, this is helium-4, and if you calculate the density distribution in the laboratory frame, it's like this, so it doesn't tell us anything. But if you do it in the Q-aligned state, then in the body fixed frame, the density distribution is like this. And if you cut here, if you look at the cross-section here, it is like this. And if you cut here to get the cross-section, it's like this. So it's almost completely isotropic, and that means it's like a circle here and a circle here. But those density profiles are obtained only after superposition. So each basis vector are like this. So this is the first basis vector, second, third, and 100th. And this is asymmetric. This is the other way asymmetric, and this is about each other. But by superposing all of them, we can obtain this. And this is quite nice. I mean, this matches well with our existing understanding of beryllium-8 structure. Then, okay, let me move on that. And to verify this kind of analysis, we can calculate energy of 2+ state by rotating Q-aligned state, and the overall probability or energies are obtained quite nicely. So this is a verification of the method. Now let me look at what happens in beryllium-10 and beryllium-12. So those are T-plot of beryllium-8, beryllium-10, beryllium-12. First of all, for beryllium-8, which is unbound, and our T-plot indeed shows this unbound feature. So this T-plot is very exceptionally stretched in this way. So this is energy minimum. And although the energy minimum is stretched because of the interaction of each basis vector, there's some concentration is here, and from those basis vectors, you can calculate intrinsic density profile of beryllium-8. So that is quite nice. Then you can move on to beryllium-10 with the same Hamiltonian, and this is a density profile of alpha cluster part. That is actually twice proton density. So we assume that in the alpha particle sector, proton density and neutron densities are equal. So we can just double proton density, and then we obtain like this. So this really like a dumbbell structure of 2 alpha clusters. But of course, in beryllium-10, we have 2 more neutrons. Then this shows how excess neutrons are distributed. Actually, this is not a very nice color, but later I'll show you a nicer color. And you can see that neutrons are mostly here and there. So they are circulating in this part like this. And if you look at the T-plot, compared to this distribution is much compressed into this part. It's still large, but it's more compressed. So this is more like normal deformed nuclei. In going to beryllium-12, interesting feature appears, namely again alpha cluster type configuration appears, but the distance between these two is a little bit larger. So beryllium-10 has the shortest axis between 2 alpha clusters, and beryllium-10 has a little bit longer axis. That's probably due to this neutron excess distribution. Now 2 neutrons are here, but 2 other neutrons are here and here. So those neutrons actually pull out those protons, then the alpha configuration is a little bit about each other like this. So beryllium-8, 10, 12 shows all alpha cluster structure, but first of all, the cluster itself is quite slightly different. In fact, this is most like a sphere, but this is a little bit ellipsoid. I mean, stretched in this way, and also distance changes. So those are quite interesting feature and to be investigated experimentally, I think. And this feature can be compared to recent paper by Shen et al. And it is very nice that beryllium 8, their result and our result are very similar. And also beryllium 10, we have comparatively similar result. But if you come to beryllium 12, you see we have more stretching like this, but in this paper, beryllium 12 is more compact like this. So in coming to beryllium 12, two approaches shows opposite trend. So this is also interesting point.
5 minutes.
Yes, thank you. This shows how basis vectors look like. So it's like almost chaotic, but we can calculate amplitude of them and we can superpose them, then we obtain a nice density profile. It looks like more ordered. And this part is cluster part, that is twice proton density, and this is a difference between neutron density and proton density. That's we define as balanced neutron density. And we obtain this, but I have shown this already. And this is second Laplace state, so it's apparently different from this distribution. Yeah. And this is about beryllium 12, same thing. And we have also those density profiles like this. Now we have this. I mean, this is just a reprise, and we divide it. Potential energy surface by those lines. So for carbon 12, we could do that. But this is not always possible. And also you may wonder that this line may be artificial thought by me. Then I'd like to show you completely different approach. That's based on the data science. In the data science, there's a so-called cluster analysis. This cluster had nothing to do with alpha cluster. Through unsupervised statistical learning. And in this approach, you have to introduce a distance between two objects. And in our case, distance can be defined like this. So this is overlap between two basis vectors. And then you can take magnitude and 1 minus magnitude. So if they are completely orthogonal, this remains 1. But if they are 1, this becomes 0. So 0 distance means they are very close. 1 distance means they are very much apart each other. So by doing this kind of analysis, you can decompose all basis vectors of the carbon 12 calculation. You can obtain region 1, region 2, region 3, and this actually corresponds to this region. This one corresponds to this region, and that one corresponds to this region. So those two independent approaches. This one is completely sort of IT type or mathematical type. So in this method, physics is not known, just mathematics or IT type. But the result is the same as consideration based on nuclear deformations. And this is called dendrogram analysis. So you can calculate the distance, and you can make a group from closest distance, next closest, and so on. So this is one group. You can set up some threshold distance. So this distance is just a little bit smaller than this. Then this group is finished here, and another group here, starting from some small distance and larger one, and so on. Sometimes this one has no counterpart, so it's just a lonely group. And by doing this, beryllium 12 basis vectors can be classified like this. And the first basis vector is right here, and it has a close friend around here. So by doing this, the first basis vector is shown to have 49% with the final eigenstate is here, and that belongs to in this group. So GP group, this group is called group 5. So group 5 is composed of those members. And by doing this kind of analysis, you can look at the decomposition of density profile into different groups. So GP5, that is the most important group, is like this. So 2 alpha clusters, and if you look at the excess neutron distribution, it's usually like this kind of thing. But also, you can have 4 neutrons in pi orbital, and that is about 40%. And this looks like alpha and broken alpha, but this one and that one has some overlap like this, so we have to investigate what the relation between them and so on. And yeah, this is excess neutron, where previous one is, oh, sorry. I'm moving the other way. Sorry. Yeah. Sorry. Yes, this is about the proton, and the next one is excess neutron. Then this is not so clear, although the density is shown in the same scale, but let me change it. Then you can see that in the group 5, you have 2 neutrons here and 2 neutrons here, but in group 2, you have 4 neutrons in this region. So this is a summary. So ab initio no-core Monte Carlo shell model can describe structure of those nuclei, and you can see some insight of alpha clustering and molecular orbiting. Besides rather precise reproduction of energies, transitions, and so on. And then you can obtain density profile in the body fixed frame. And I discussed this already. And beryllium-10 is di-alpha cluster system plus pi orbital 2 excess neutrons. But beryllium-12 is again di-alpha cluster. But this cluster and this cluster, they are a little bit different. And plus various molecular orbital configurations. But in some works, beryllium-12 has been described as standard ellipsoidal object, but our work shows that di-alpha cluster structure is still there. And this unsupervised statistical learning is quite useful to obtain those understanding. So just taking the last 1 minute, let me make one advertisement. This is our paper. This paper was published just 2 days ago. That's about nuclear shape and rotation. And in this paper, we are stating that the actually symmetric shape, like rugby ball, may not be proper picture of nuclear ellipsoidal deformation. So atomic nuclei are like almond, so it's a little bit suppressed in this way. So if you have time, please look at this paper also. Thank you very much for your attention. Yeah.
Thank you for the interesting talk. Have you compared, I mean, you showed the density profile from beryllium-8 up to beryllium-12.
Yes.
Have you compared the beryllium-12 with helium-8? Because it looked for me that in the middle you have 2 alphas, but helium-8 seems to have a very similar configuration.
Yes, that's a good point. Let me come back to that slide. Yes. Okay, yeah. So this is a 3.7 femtometer. This is still smaller than that because we have the same scale. So this has rather longest distance. This is the shortest. This is in between, but maybe closer to that. So this unbound nature of beryllium-8 is rather important to determine the distance of two alpha cluster. Although the calculation was made in the bound state approximation.
Yeah, I was just wondering about the last one.
Yes?
To the right.
Yeah.
I mean, if you have the two alphas and the neutrons on
Yeah.
the top.
Yeah.
I mean, the last one.
This one?
This looks for me a lot as helium-8, if I'm interpreting correctly.
Yes.
Yeah, you have this a little bit red. Are the neutrons or not?
This is,
Helium-8. Yeah, because
this is the barium
when you
8.
su-
This is
helium-8,
barium 12.
yeah,
And those are two alphas.
yeah.
And those are 4 neutrons. And 2 of them are in this region. But the 2 of them are here or there.
The yellow ones are alphas or no?
No, they are also neutrons. They are just the color code of the density.
Yeah, but these are the alphas.
Yeah,
corresponds
no,
to
those
the
are
position.
excess neutrons. They are only about excess neutrons.
Ah, okay. So you
This is
cannot see the alpha.
this is actually proton twice proton density. That shows how nucleons making alpha are distributed. So it's very interesting. Yeah.
So I was wondering why you're not looking at nuclei like beryllium-9 and beryllium-11. Is there a problem? Is this more complicated of doing the calculation?
Yes, I think I agree that we should do that. And there are some preliminary results, but we have a little difficulty to have a proper manpower. So I agree completely with you. We should discuss beryllium-9, beryllium-11, and also other things. But this is computationally heavy, but also the analysis is heavy for human part. Yes.
So I have a question.
Yes.
When you have these different configurations, when you go from one to another, so did you look at the single particle levels? Because this is like a diabatic transition, so there must be level repulsions, and you could see some interesting things just by looking at how the level repulsion occurs when you go.
Okay, yeah. That should happen if you calculate a deformed single particle orbit. And I understand, but we haven't done it. But of course, the nuclei are distributed over not only the lowest orbital, but the second or third orbitals. And I don't think I have a figure for that, but it's distributed, of course, yes. Otherwise, we don't reproduce carbon-12 Be2. That is quite enhanced. So you cannot describe it only with P-shell.
Right.
Yeah.
Any more questions? I think we are running out of time, so we have to move to a discussion. There will be more questions for you, for sure.
Okay.
If you stay around, if you don't disappear.
Yeah, I'll stay. Yeah, of course, of course.
Okay, let's take the
Okay,
speaker.
thank you.